section 3.4 continued, vertical stretches and compressions, and we're also going to talk about horizontal stretches and compresses. So just as a reminder, horizontal movements change your x values, and vertical changes your y values. So the first thing we're going to concentrate on is the vertical stretches and compressions. So remember that we had our equation that we use. We're going to use y equals c times your function f of x. So if c is a positive number, then you're going to stretch when c is greater than 1 away from the x-axis, and you're going to compress it when c is in between 0 and 1 towards the x-axis. So for this, remember that we also should note that this should be the absolute value of c, because remember the negative is going to be reflecting it. So if we look at our graphs here, for the first one, we're going to do let x and y shown in the tables below represent the parent graph coordinates. So here, if you'll notice, these are the parent, and these is this parent right here. And of course, what's the parent graph for this function that we're graphing? Y equals the square root of x, which is already graphed on your paper. So now that we have that, let's go ahead and take a look at this. So I already have some parent graph points in my table, 0, 0, 1, 1, and 4, 2. So remember that we said when we're doing this as a vertical transformation, we are going to be changing our y values. So since this value is right here, that 2 is above 1, we know that this is going to be a vertical stretch by a factor of, in this case, 2, because that's the number on the outside. So we're going to take our y values and we're multiplying them by 2. So 2 times 0 is 0, 2 times 1 is 2, and 2 times 2 gives me 4. So now we have our new coordinates for our graph. So the new coordinates are going to be, we have 0 from x from our original parent graph because we didn't change our x values, and our new coordinate 0. So then we have 1, 2, and then 4, 4. So that's one way to look at this, and then I can plot those points. Or I can just go ahead and actually look at my graph. If I look at this graph that I have here, again, I'm taking my y values and multiplying them by 2. So if I look at 0, 0 times a y value of 0 times 2 would be 0. Then I have a y value of 1 right here. So 1 times 2 gives me 2. If I have the next value, which is nice, which is right here, so I have a y value of 2, so 2 times, in this case, sorry, I should make that red, so 2 times 2 gives me 4, so then I know the next value up here is at 4. And if I keep going, if I did of the y value here of 3, I know that 3 times 2 is going to give me 6, so this would be 3, 4, 5, 6 right here. So this graph that I'm graphing is g of x. And what did we do? We took our y values and we stretched them up away from our x-axis. That's why it's called a vertical stretch by 2. So then let's go ahead and look at the next one. So the next graph that we have, our parent graph, again, values are 0, 0, 1, 1, 4, 2. And if I look at this value here, it's in between 0 and 1. So it's because it's a fraction, this is going to be a vertical compression by a factor of 1/2. So with that, now I can take my y values from my parent function and I'm multiplying them all by 1/2. So 1/2 times 0 would give me 0. This would be 1/2. And 1/2 times 2 would be 1. So the new x and y coordinates for your transform graph would be 0, 0, 1, 1/2, and 4, 1. So now if I take these from my graph and look at it, then I'm taking my y values again from my parent function. So 0 times 1/2 is 0. 1 times 1/2 gives me 1/2. If I take this next y value of 2 times a half, I get 1. And if I take 3 times a half, I would get 1.5, even though we didn't do that on our chart. And so this would be my function for h of x. And notice that our values were being compressed down. That's why it's called a vertical compression, because we're bringing the values down towards our x-axis. So then for the next part, well, let's just go back up to the other one. So for this one, again, I just wanted to take note that our x values stay the same. We were only changing our y value. So I'm going to note that up at the top. So note x values stay the same. Y values are the ones changing. All right, so let's go ahead and take a look at the next graph, and we'll do that one in class. So we're going to go to the next page and look at horizontal compressions and stretches. So horizontal compressions and stretches, the difference is now notice that a value that we have for the function y equals f times ax, notice that a is attached to our x. Since it's attached to our x, that's what tells me I have a horizontal compression or stretch depending on what the a value is equal to. And remember, we said that horizontal movements change your x values. So for this, if I look at my first graph that I have here, so if my a value is in between 0 and 1, and I should say that again, the absolute value should be right there, then we know it's going to be a horizontal stretch away from the y-axis. When the absolute value is greater than 1, it's going to be stretched towards the y-axis. So this is the opposite thinking that I was talking about the other day. So let x and y that's already shown in the tables below represent our parent graph. So this is the parent coordinates, and this is the parent coordinates. And what is our parent function? So our parent function is over here, which is y equals the absolute value of x. So for this first one, we have a 3. So we said that if it's greater than 1, our a value, I know it's going to be a horizontal compression by a factor of 1 over our a value. So in this case, 1/3. So horizontal, if I said, so horizontal compression by 1/3. And remember, we said before, when you're horizontally changing something on your graph, you're changing your, in this case, so you're going to change your x values, your y values are going to stay the same. So notice that here at the top of my graph, I put the opposite of what I think goes there. So instead of putting 3x, I put 1/3 x, and then I try to plug in numbers. So 1/3 times 0, because that was our original parent graph, gives me 0. 1/3 times 1 is 1/3. 1/3 times -1 is -1/3. And 1/3 times 3 gives me 1, and 1/3 times -3 gives me -1. So let's go ahead and look at this on our graph. So basically what we're doing is we're changing our our x values by 1/3. So if I look at my parent graph, I'm going to pick out some x values here. And I'm looking for x values that are easily, even though 1's not easily divisible by 3, we did that in our table, which is why I picked that. So 9 would be good, and 6 would also be a good point to use. So what I'm going to do is I'm going to take those x values and I'm multiplying them by 1/3. So I have 0, 0 on my graph, and then we get now 1/3, 1, which is here. We have -1/3, 1, which is on the opposite side. Then we had 1, 3, which would be right here, and -1, 3. So notice that we took this x value right here, and we multiplied the x value by 1/3 keeping our y value the same. So then over here, if we multiply this point by a third for the x value, 6 times a third is 2, so I know this is going to be here at 2. And then we have an x value of 9 here, so 9 times 1/3 would give me 3. So this is going to move into 3. And if I do the other side, notice that now I get my graph. Get my ruler and do my points here. And for my graph, notice that it's a horizontal compression by 1/3 because we're compressing our graph towards the y-axis. So our new coordinates, which I'm actually going to write on the other side since we're changing our x values, so these would be the new x and y, would then be 0, 0, 1/3, 1, negative 1/3, 1, 1 comma 3, and negative 1 comma 3. So those were our new values that we used. And again, notice that our y value stayed the same. We only changed our x value. So I'm going to put that note over here. So note y values stay the same. Change x only, since we're only doing horizontal stretches and compresses right now. So then for the next graph, if we look at it, we have the absolute value of 1/3 times x. So for this one, since it's 1/3 is in between 0 and 1, I know this is going to be a horizontal stretch by a factor of 1/1/3, which is really equal to 3. So we're stretching out our x values by 3. So I'm going to do this by the graph this time first, and then I'm going to make the table. So looking at my graph values that I have here, if I have an x value, well, first I'll start with 0. If I have an x value of 0, 0 times 3 is 0. If I have an x value right here of 1, 1 times 3 would give me 3, which would be right there. Now if I take this x value here, that's an x value of 3. 3 times 3 would give me 9, so that's going to be all the way on this side. So then I would do the corresponding points on the other side. So this is going to be negative 3, because negative 1 times 3 gives me negative 3. And this point right here would be negative 3 times 3, which would give me negative 9 going there. So now if I draw in my graph, I have my absolute value shape going this way. So this one and this one. So that right there is our function for h of x. The other one was for g of x. And notice that what did we do? We stretched our values going this way, now away from the y-axis. That's why it's called a horizontal stretch. So if I look at my table, I would do the opposite in my table. So instead of putting 1/3, we put 3x. So if I multiply all my x values by 3, 3 times 0 gives me 0. This would be 3 times 1, which is 3, negative 3. This would give me 6 and negative 6. So my new coordinates are 0, 0, 3, 1, negative 3, 1, 6, 2, and negative 6, 2. So those give me the new values that I have. So I'm going to pull up my graphing calculator just to show you a different kind of graph so you can kind of start seeing this a little bit better. So on my graphing calculator here, I have this program that I can use to show you what that A value and that C value are doing, and that's different. So I'm using a sine graph, which we'll learn about later on during the year. So for right now, this is what it looks like for our parent graph for sine. So for this, if I change this A value, which means, remember, those are the changes in X. If I look at that, you'll notice that we're going to either stretch or compress it away from the y-axis, and the C value here is going to be changing my y values away from or towards the x-axis. So I'm going to look at my C values first. So here's my C value. My C value of 1 right now. So the larger I get, notice that if I do a C value by 2, I get this graph that's right here. So what did we do from our parent graph? If I go back, we stretched it up by a value of 2. If I do 3, notice that I would get an even larger graph. So this one would be a vertical stretch by 3. And if I go back to my parent graph, which would be right here, so I'm going to graph that in blue. So my parent graph, if I now do something that's in between 0 and 1, so I'm going to go, oops. So I'm going to make my C value maybe 0.5. Notice that it vertically compresses it now. It's smaller than the graph in blue by a factor of 1/2. So we took all our y values and we multiplied them by half, but we kept all our x values the same. We didn't change the x, we just changed our y values. So that's for that C right here. So that's what we just did. So I'm going to erase this, and then let's go ahead and look at what the A does on our graph. So I'm going to go ahead and go back to my parent graph. So I'm going to draw that in blue. So this is my parent graph. So if I make my A value change on my parent graph, so I'm going to take this A value and I'm going to do, let's say, 0.5. So remember, if I make my A value 0.5, this is opposite thinking. So that means I'm going to horizontally stretch my graph by a factor of 2. So if I hit enter, notice that I took those x values that we had right here and I stretched this out by 2 because this is going to be right here. So I stretched it out. And so now my graph is just about half of what we saw before. So that would be a horizontal stretch, again, by a factor of 1 over 0.5, which is 2. So then let's go ahead and put in a value of 2 instead now and see what happens. So if I plug 2 into my graph, now notice that my graph looks like we have compressed it in towards the y-axis, and now we're showing 2 graphs, where previously in the blue graph we only had 1 cycle. So now see that we have, within one parent graph, we have now 2 cycles. So that graph in red is why we have, when we change this value here to 2, a horizontal compression by a factor of 1/2, because we cut it in half of what our parent graph was originally. So notice that half of our parent graph is now 1 cycle. And so we'll talk about that later in the year. I just wanted to see why it's different for the horizontal stretches and compresses. And we'll talk about those 2 graphs in class that we did not get to in these notes. So just make sure that you have them done and bring with you to class.